So welcome to the lectures of Power System Dynamics and Control course. So last class we discussed small signal stability analysis of a single machine infinite bus system considering the classical model. Okay. So as we'll increase or we'll consider other models, the complexity will increase obviously because we need to linearize all the equations, then put together, then the order of the system matrix will increase obviously. For even for single machine system, the order will increase itself. So therefore our study will be limited to this classical model. Then another model we'll discuss, that is the little higher version of that model, that is called as one axis flux decay model. Okay, so that we'll consider in this lecture for formulating the system matrix and how we can model a small signal or linearized model for small signal stability analysis. We'll see in this lecture. Okay, so here also we are considering small signal stability analysis of single machine connected to infinite bus system, but here we'll consider one axis flux decay model. That is, already we have discussed the model, one axis flux decay model, just simplifying, considering few assumptions. Okay, and here this is the model. We can see this is your terminal voltage, this is terminal current in dq axis frame of reference, and when it is transformed to the common reference frame, we are multiplying e to the power j of delta minus pi by 2, right? And this machine is connected to infinite bus, where the magnitude of the infinite bus voltage is V infinite and the angle is 0. Obviously, we are taking the infinite bus as a reference bus. So it is connected through some transmission lines, and the equivalent reactance and resistance of the transmission line is given Xc and Re. Okay. So let us here assume the input mechanical torque Tm be constant, and the turbine speed governor dynamics need not to be considered here. Even if you can consider this speed governor model, but here for simplification of analysis, we are neglecting the dynamics of, because we are assuming Tm as constant, so therefore we are neglecting. So let the generator be represented by one axis flux decay model. Okay, already we know the model, so the DAE or differential algebraic equation of the flux decay model, excluding excitodynamics, can be given as this, right? Excluding excitodynamics, these three will be the differential equation, and these are the terminal voltage equations, right? VD and VQ. And obviously T we know, already we derived, T is the real of this, the real of the power equation. This is your internal EMF, this is your terminal current, and dq axis. And after finding the real part, we saw that it will be EQ dash IQ plus XQ minus XD dash IQ ID. This is already we have derived in your previous lectures, right? So from the figure now, the generator current can be written as this. The terminal current or the injected current from the generator, if I'll write, it is nothing but the voltage at this point minus voltage at this point by divided by the equivalent impedance of the transmission line. So this is what it is mentioned here. So your terminal current referred to the common reference frame ID plus JIQ to the power J of delta minus pi by 2 is equal to, that is the terminal voltage VD plus JVQ e to the power J delta minus pi by 2 minus V infinity e to the power J 0. divided by Re plus JXE. This is the equivalent impedance, right? Now, and further simplification and separating the real and imaginary parts from this equation, we can obtain these two expressions. One is your real part, one is your imaginary part, right? And now, if in order to linearize these equations, what do we need? We need the initial conditions. So let us assume the steady state operating point values of these EQ dash, delta, EFD, ID, IQ, VD, and VQ be represented as this. Okay, EQ dash 0, delta naught, EFD naught, IDO, IQO, VDO, VQO, right? So these are the initial values. We are using these initial values. We will linearize these equations in order to get the linearized state space model. Okay. So now linearizing this equation, and these are algebraic equations. Now we are linearizing the algebraic equations. Then we'll linearize the differential equation. So another set of algebraic equation already we found in the previous slide, that is these two equations, and another set we found from the terminal current equation, right? So now we have two sets of algebraic equation. Now if we'll linearize these two, both these equations, what we'll find, if we'll first linearize this set of equation, then I'll find this, right? Delta VD, delta VQ will be nothing but equal to this matrix consisting of RE minus XE, XE RE multiplied with delta ID, delta IQ plus V infinite cos delta naught minus V infinite sin delta naught delta delta. Because in order to linearize, I have to take the derivative of these expressions. So therefore, after taking derivative and substituting the initial values, I get this. Okay, cos delta 0 and sin delta 0. Okay. So now if we linearize this set of equation, I will get this equation, right? Delta VD, delta VQ will be equal to this. Okay. You can do this. It is easy. Now we can see this two set of equation where the left hand side is equal, right? Now if we'll equate the right hand side, so since the left hand side of the linearized equations are same, we can equate the right hand side of the equation. After equating, we can find delta ID and delta IQ. Just after equating the right hand side of this equation and right hand side of this equation, I can eliminate delta ID and delta IQ, right? So from this equation. So I can find now delta ID and delta IQ, that will be nothing but this RE minus XC plus XQ, XC plus XC dash RE inverse 0 delta IQ dash plus minus V infinity cos delta naught V infinity sin delta naught multiplied with delta delta, right? So now just little simplification if we'll do, I can find out the inverse of this matrix, right? If I'll find the inverse, this is nothing but the adjoint matrix divided by the determinant of the matrix, and that will be multiplied with this, because if I'll manipulate this whole this part of the equation, I'll find this, right? Just manipulating, I'll get this. Okay, I'll get this whole equation, in fact whole this part, right? So now I can find, just multiplying these two matrices, right? I'll find this equation multiplied with delta delta and delta IQ dash, right? So now this is one set of linearized equation we found from the algebraic equation. Now we need to find the linearized differential equation. So in order to find that, let us linearize the differential equations. So we had three differential equations concerned with EQ dash, delta dash, delta and omega, right? Now linearizing those equations, obviously I found this equation, right? Linearization means we know already through the Taylor series expansion how to linearize. So just doing that, we found this equation delta eq dot delta eq dash dot delta delta dot delta omega dot will be equal to this into this. Now these are the state variables, present state variables. And this matrix into delta ID delta IQ, this into delta EFD delta TM. So delta TM, delta EFD, they're considered here as, currently they're considered as the input. Delta TM obviously we are assuming constant, will later it will be neglected, but now we can consider it as constant, right? Sorry, the input, okay? And EFD also because now we have not considered the excitodynamics. When we will consider the excitodynamics, this EFD also will be replaced, right? Because EFD is nothing but it is the field exciter voltage, right? Exciter voltage. So it will be replaced soon because till now we have not incorporated the excitodynamics in this equation, right? Okay. So when the excitodynamics will incorporate, this will also be neglected. Okay. So now let us eliminate this first because delta ID delta IQ is a intermediary. It is not also a state variable or not the input variable. So therefore we need to eliminate this delta ID and delta IQ because here we have the equation for delta ID and delta IQ in terms of delta delta and delta EQ dash. These are the state variables, right? So now I can substitute this delta ID and delta IQ in this equation, right? So if I'll substitute this whole equation instead of delta ID and delta IQ, I can find the whole state variable differential equation in terms of state variables and the input variables, right? Now you can see your equation will be simplified to this form where few constants are there. We can find the values of this constant like this: k1, k2, 1 by k3 and k4. So this constant, the expression of each of the constant is like this, okay? k1, k2, k3, k4. So now we can see this is now the state space model where the excitodynamics is not incorporated yet. This EFD represents the output of the exciter, but input to the exciter is V reference, which is not yet incorporated, right? So now let us incorporate the excitodynamics. So okay. So a simplified fast acting static exciter is now considered, okay, which is represented by a first order control block with a gain of K and time constant TA, as we can see it in the figure here, right? Here the transfer function model for this fast acting static exciter will look like this: K by 1 plus STA, and your output will be EFD, and the input to this is VT minus V reference. V reference is the reference voltage and VT is the terminal voltage, measured voltage, terminal voltage, right? So now if we'll write the differential equation for this block, it will look like this, right? Already you have seen this equation previously during modeling of the exciters, right? So it will become TA d of EFD by dt equal to minus EFD. Obviously we can derive it from this block diagram as well, plus K into V reference minus VT, right? So this will be your differential equation. Now just linearizing this, I will get TA d by dt of delta EFD, that is equal to minus of delta EFD plus K delta V reference minus delta VT, right? So delta VT is your terminal voltage, change in the terminal voltage. And we know the terminal voltage is equal to Vd square plus Vq square square root. This we know from the beginning. And just taking the, just linearizing this equation for terminal voltage, we'll find delta Vt will be equal to del Vdo by Vt. Just take the derivative and substitute the initial values of VDO and VQO. we'll found VDO by VT delta VD plus VQO by VT delta VQ, right? And in the matrix form, if we'll write it, it will become VDO by VT, VQO by VT multiplied with VD delta VD delta VQ, right? Now we know this equation delta ID delta IQ if and also delta VD delta VQ from previous equations, right? Now if I'll substitute delta ID delta IQ here in this equation, then your equation will look like this. Your delta VD delta VQ equation will look like this, right? So your delta VD delta VQ equation is this. Now delta VT in terms of delta VD and delta VQ is this. Now if I'll substitute delta VD and delta VQ here in this delta VT equation, I can find it as, just simplifying it, we'll find it is equal to K5 delta delta plus K6 delta EQ dash. So K5, K6 are constants, right? So just substituting this, we'll find this. So K5 and K5, K5 and K6 are this. The expression for K5 and K6, right? Now if we'll see the previous state space model till what we have derived, excluding the exciter model, this is your state space model. Excluding the state space model, sorry, excluding the exciter model. Now if we'll consider the exciter model, your exciter model is TA into d of dy by dt of delta EFD equal to delta EFD plus this, already we know. And if I'll substitute this, okay, already we know this also VT equal to K5 delta delta plus K6 delta EQ dash. This I can substitute here in this equation instead of delta VT. So if I'll substitute here in this equation, then I'll substituting this, and again I'm making an equation, another equation here, putting another equation here. This will become a 4x1 and 4x4 equation, fourth order equation it will become. Now you can see the constants K1 to K6 are called Heffron Phillips model because it was, this model was in fact developed by Heffron Phillips, and therefore these constants K1 to K6 are called Heffron Phillips constants, and the state space model given by this model is called Heffron Phillips model. And now the complete Heffron Phillips model will look like this. Now if we'll substitute, if we'll embed this equation, this equation of the exciter model in this state space model, substituting delta VT here in this equation, now your complete state space model will look like this. This is the complete state space model for the one axis flux decay model, right? One axis flux decay model, okay, model where the turbine dynamics is not considered, right? So here we can see the complete state space model, right? It will look like this. It is a fourth order system now. Okay, so this is your complete state space model. So now if we'll convert this equation, this above equation, this state space model into Laplace domain, we'll get the following set of equations, right? Just you can do this, we'll get this another set of equation in the Laplace domain. And if we can find the block diagram for this set of Laplace equations, your block diagram will look like this, right? Obviously you can do this. This is very easy. So this model is known as Heffron Phillips model. Okay. So this model mostly people use for analyzing a single machine infinite bus system, considering the flux decay model. Okay, Heffron Phillips model. Okay, so this is what we can see, the Heffron Phillips model. So this model we have seen. This is your sorry, this already we discussed, right? So how if it will be embedded in this part, of the equation, then we'll get the complete state space model. This model is known as Heffron Phillips model, right? And also we know how we'll get the equations in the Laplace domain, right? Now if we'll simplify these equations in the Laplace domain, this little simplification if we'll do, we'll find delta EQ dash will be equal to this, delta EF ds will be equal to this, and delta omega s obviously equal to this, del s delta s. Now just assuming this v delta v reference equal to 0 and substituting here this delta v reference equal to 0, we'll find more simplified equation, right? And finding, sorry, again substituting delta EFD here in this equation, right? Then we'll find this equation, right? So your delta EQ dash equation will become, in terms of delta delta S, will become like this, right? Okay. So now the linearized electrical torque delta TE, we can write it as this. This is your electromagnetic torque equation. If we'll linearize this equation, we'll find this. Delta T will become equal to uh, this equation, right? Delta EQ dash into IQ plus EQ dash delta IQ plus XQ minus X3 dash IQ delta ID plus XQ minus X3 dash ID delta IQ, right? So now just manipulating, we'll find in terms of, if we'll write this equation in terms of delta ID and delta IQ, this equation will look like this, right? And we know this equation already we have derived for delta ID and delta IQ. If we'll substitute this equation for delta ID and delta IQ in this electromagnetic torque equation, linearized electromagnetic torque equation, we'll find this equation, right? So it will be delta T will be equal to K1 delta delta plus K2 delta EQ dash. So now if I'll convert this into the Laplace domain and substitute delta EQ dash equation already we have, and if we'll substitute this in this equation, right? So then it will look like this. Delta T, if we'll write in the Laplace domain, it will look like this. Delta Ts will be equal to this. Okay. So this is your transfer function into delta delta S. So now here if we'll see delta Ts will be equal to Hs, if we'll assume this transfer function as Hs into delta delta S, right? And we know this equation S square delta delta S, okay? And if we'll substitute this now, delta EQ dash here and delta T dash here in this equation, and again we'll substitute delta EQ dash here in this equation and consider delta Tm as equal to 0, then we'll find this kind of characteristic equation. Okay. So now delta Tm equal to 0 means it is the input is like we can say that this is a autonomous system having no input, right? Okay. So the small signal oscillations are typically in the range of 0.1 Hz to 3 Hz. In this region of frequency interest, the transfer function Hs can be split into two components. Now this transfer function can be split into two components. So if we'll say, so Hs is this, from this equation, your transfer function is this Hs, right? Now we want to split this Hs into two parts. So if we'll just do a little manipulation, then and neglecting the effect of the constant K4, we'll find this equation, right? So now we can see here, if we'll just manipulate and just segregate into two parts, we'll find this is one part, right? This is known as Ks, and this is another part which is known as Kd, right? So therefore I can write it here, Hs equal to nothing but Ks plus Skd, okay? So S is j omega, so therefore I can write Hs is equal to Ks plus Skd. So now if we'll write the equation for delta T, that will become Ks plus delta S plus j omega Kd delta, right? So that I can write Ks delta delta plus Kd, j omega delta delta is nothing but it is delta omega, right? Okay. So the electrical torque has now two components. One is your synchronizing component, okay, and other one is your damping component, right? So this is called the synchronizing component or synchronized torque, and this is the damping torque, Kd delta omega. So synchronizing torque Ks is in phase with the change in the rotor angle delta delta, and the damping torque is in quadrature to the change in the rotor angle or in phase with the change in the speed, right? So in quadrature, because it is multiplied with j omega into delta delta, therefore it is in quadrature. It is making an angle of 90 degree with delta delta. So therefore it is in the quadrature to the change in the rotor angle or in phase with the change in the speed, right? So now your characteristic equation will look like this: s square plus omega base by 2h ds plus omega base by 2h hs into delta delta s, right? So now if we'll substitute hs here, hs is equal to ks plus skd. If we'll substitute, it will become s square omega base by 2h d plus kds, because we have substituted sh hs as ks plus skd. So therefore your characteristic equation will look like this, right? So now with this characteristic equation, s square plus omega base by 2h d plus kds plus omega base by 2h ks delta omega s equal to 0. It in fact represents a damped second order unforced system, right? It is unforced system, as already we have discussed this, because Tm delta Tm is become 0, right? So we assume the input torque is constant, so delta Tm becomes 0. So if the damping coefficient d plus kd is not considered, then the system becomes undamped, right? If it becomes 0, this d plus kd, then your system becomes undamped with natural frequency of oscillation that is given by this omega base by 2h into ks square root plus minus j, right? So in case the damping coefficient d plus kd becomes negative, in case it becomes negative due to system conditions, then there will be oscillatory instability. If it becomes negative, what happens? Whatever root will get, the roots will have the positive real part, so therefore it is oscillatory instability, and that will lead to in fact keep on increasing. This oscillation will keep on increasing and it will lead to loss of synchronism, right? So if both the synchronizing and damping torque are positive for a given system, then after the disturbance, the system will settle down to a steady state operating point. If both are positive, right? With oscillation damped out. The constant K5 becomes important while assessing the stability, because this Kd and Ks both are functions of K5. So therefore, this constant K5 becomes important while assessing the stability. So you know Ks is equal to this, right? And Kd equal to this. Both are functions of K5, right? We can see here. And in fact, from the above equation, it can be observed that if K5 becomes negative, then for a practical system, the synchronizing coefficient Ks becomes positive and increases as compared to K5 being positive. K5, the synchronizing torque improves. So negative K5 in fact helps in increasing the value of Ks, and hence the synchronizing torque improves. But if the K5 is negative, then your damping coefficient Kd becomes negative, right? When Kd becomes negative, it leads to the negative damping torque and hence oscillatory instability happens. So therefore we can see if this K5 impacts in both way, when K5 is increasing, what happens? Your Ks improves, whereas Kd hampers. Your Kd becomes like it gives a negative damping torque. So the effect of negative damping torque due to negative K5 gets pronounced if the exciter has a very high gain K. So this K5 is in fact, it becomes pronounced because K5 is a function of K. So if the exciter has a high gain, very high gain K, then obviously your K5 gets pronounced, right? So in practical system, K5 can become negative in a heavily loaded condition, right? Where most of the time when the system is heavily loaded, so this K5 constant becomes negative, and a high gain exciter can lead to system stability issues, right? Right. So if you're under the highly loaded case, your K5 becomes negative, and again if your exciter has a high gain, right, that will lead to system instability. So the physical understanding of this is that a high gain exciter can build up the terminal voltage rapidly after disturbance. Okay. In fact, it is very essential, the high gain exciter, in order to maintain the voltage, right? And it also improves the synchronizing torque, but at the same time, it has a negative damping, right? Because of high gain and highly loaded condition, your K5 becomes negative, and that lead to the negative damping condition, right? And therefore, due to its high gain, it amplifies a very small error in the terminal voltage without enough system damping, can lead to oscillatory instability, right? So now this is very important, and we can analyze this through this example. You can do this example. You can consider this example as one of the assignment. I will send this. Just you do this. So this is there are following two systems, test system. In one test system, the K1, K2, K3, K4, K5, K6, these constant values are given along with other constant TDO dash, H, TA, and D. And similarly, other test system is given where K2, K1, K2, K3, K4, K5, K6 is given. In one test system, K5 is considered positive, other test system K5 is considered negative. And so therefore, it is mentioned that find the eigenvalues for K equal to 50. Considering K equal to 50, we need to find the eigenvalues and also plot the root locus to study the system stability for varying K. And notice that in the system 1, the value of K5 is greater than 0, and system 2, it is K5 is less than 0. So what we need to do, this I will send again as assignment 3. Here your constants are given for two systems. We need to find the eigenvalues from the characteristic equation for K equal to 50. And you have to plot the root locus to study the system stability by varying the K. You'll vary the K and you'll find the system stability through the root locus method. Okay. And also you find the range of the values of K5 for which the system will be stable, and also find the critical value for K5. Determine the participation matrix and time domain response of the states for an unforced system. I hope you can find this because already we have the state space model, and you can find the participation matrix and the time domain response of the states. Okay. So this you have to make using the MATLAB program, and you have to submit it. Okay. So I will send this to, this is a single machine infinite bus system as we discussed the theory. Okay. Infinite bus system, considering the Heffron Phillips model, you have to do this analysis. Okay. Heffron Phillips model, you have to do this analysis, and submit it. Okay.